from agenda, please, Mrs. Trân Thị Lượng. Trân Thị Lượng, please.
Ladies and gentlemen, my name is Trân Thị Lượng. Firstly, I would like to thank the MCO 2021 committee for giving me this wonderful opportunity to present our research today. It's a great honor for me to be here to present our work. Our team has 3 members, Dr. Nguyễn Ngọc Cương, Dr. Bùi Đức Trình, and me. We are all from Academy of Cryptography Technique. And now I will present our research about 4x4 recursive MDS matrices effective for implementation from reasonable code over volatile sub-Q.
Excuse me, Ms. Lượng, show your slide, please.
My presentation has 4 sections. The first section is introduction. The second section we will present related works. The third section is our main result. We will show you the way to obtain 4x4 recursive MDS matrices effective for implementation from reasonable code. And the final section we will show the conclusion. As we know, MDS matrices are from coding theory. They play an important role in block cipher design, especially SPN block ciphers. MDS matrices have been used as a diffusion component for many block ciphers, such as AES, Shark Square 2-Fitch, Manta Hieroglyph, Camellia, and Mugi Stream cipher, and Whirlpool cryptographic hash function. As we know, MDS matrices has very important role for design of many ciphers, so they can use for many any ciphers in practice. Building MDS division layers with low implementation costs is a challenge for the designers, and the low cost constructing of MDS matrices with its inverse is another important issue. So we can see in practice, designers want to build MDS matrices and the MDS matrices of inverse. So they want to obtain low-cost construction of MDS matrices. This is a great challenge for the designers. As we know, recursive MDS matrices are recently interested into many researchers because they can be power of a serial matrices, so they can be suitable for limited and constrained environment. Recursive MDS matrices have been studied by many authors in the literature because of its important application in lightweight cryptography. For example, in the reference from 3 to 8. However, according to these studies, searching for such recursive MDS matrices requires performing an exhaustive search on the serial matrices family. This will limit the size of the found MDS matrices. Or it is to have to use some other rather complicated methods such as PCH code. For example, in the reference 7 and 8. And in this research, we will show you the way to obtain 4x4 recursive MDS matrices effective for implementation from reasonable code over a general field called field sub Q, for Q equal to P to the R, and P is prime number. Now I will show you the section 2. We will show some related works relevant with our research. The first, I will introduce about the recursive MDS matrix. The definition of recursive MDS matrix is that let A be an MDS matrix with the elements that belong to the Guala fields of P to the R. A is called a recursive MDS matrix as the power of a serial matrix if there exists a serial matrix S of psi M, with M is greater than or equal to 2 over Guala fields of P to the R, such as A equal to S to the M. where the serial matrix S associated with a polynomial Cx has the following form. You can see in the form of the serial matrix, they have almost the elements equal to 1 and 0. They have only the last row with non-zero elements. So they can suitable and very meaningful for hardware implementation. And we can see also the inverse of the serial matrix. They have the same form, but instead of the last row, it has the first row with non-zero elements. And some authors in the literature, they want to build some MDS matrix. They use the serial to the M, and they verify the MDS condition. And some serial to the M may be an MDS matrix or not. Now I introduce about the reasonable code. An IS code over the fields of Q, where Q equal to P to the M, is a BCH code of length N equal to Q minus 1. Suppose alpha is a primitive element of the field. IS code of length N equal to Q minus 1, designed with distance D, will have a corresponding generating polynomial of degree D minus 1, as follows. This is the form of generating polynomial, where B is a pre-selected value. B belongs to the N set, and B is greater than or equal to 1. For constructing symmetric MDS matrices using RS code, in the reference 10, we show the symmetric recursive MDS matrices from the RS code over the specific fields, fields of 2 to the 4 and fields of 2 to the 8. And we stated and proved two propositions. The first position, we state that on constructing 4x4 recursive MDS matrices over fields of 2 to the 4 and fields 2 to the 8 from RS codes, the generating polynomial Gx of the form 1 is a symmetric polynomial having the constant term equal to 1 if and only if B equal to 6 or B equal to 126 respectively. And the proposition 2, we state that on constructing H for H 16 for 16 or 32 by 32 recursive MDS matrices over fields of 2 to the 8 from IS code, the generating polynomial Gx of the form 1 is a symmetric polynomial having the constant term equal to 1 if and only if B equal to 124 or 120 or 112 respectively. So you can see in this research, we show the exactly value of B. B is the coefficient of the polynomial Gx. And with the B value, we will obtain the recursive MDS matrix with the symmetric property from the IS code. But we didn't show the value of B, and we don't show the way to obtain recursive MDS matrices with the symmetric property from the general field, general field of Q, where Q equal to P to the R. And now in this research, we will solve this problem. And now in the section 3, we will show the way to obtain 4x4 recursive MDS matrices effective for implementation from reasonable code over a color field of Q, the general field. To construct a 4x4 MDS matrix from RS code over the fields of Q for Q equal to P to the R, where P is prime number and R is greater than or equal to 2. We build an IS code with the generating polynomial Gx of degree 4 and has the following form. This is the form of the generating polynomial, where B equal to, where 1 is less than or equal to B and B less than and equal to Q minus 1, and alpha is a primitive element of the field. we expand gx and we obtain the form of the polynomial gx as follows in the equation 3. So you can see if you want to obtain the gx symmetric and has a constant term equal to 1, we must have the constant term equal to 1 and the coefficient of x cubed and coefficient of x must equal to each other. So we have the equation in 4. Then from the equation 4, we state the proposition 3. We state that on constructing 4x4 recursive MDS matrices from RS code over fields of Q, for Q equal to P to the R, and P is prime number, and R is greater than or equal to 2. The generating polynomial Gx of the form 2 is a symmetric polynomial having the constant term equal to 1 if and only if P equal to 2, and there are two cases, R equal to 2 and B equal to 3, or R is greater than or equal to 3 and B equal to 2 to the R minus 1 and minus 2. And the meaning of the proposition, you can see that if P equal to 2, we can obtain the symmetric recursive MDS matrices from the RS code. But if P is not equal to 2, we cannot obtain the symmetric recursive MDS matrices of size 4 from RS code. This is the main result in this research. And we prove this proposition, but we have no time to present it. If you are concerned and attend this proposition, you can contact me by email. And from the proposition, we have some examples. For Q equal to the third, B equal to 2. For Q equal to the 4, B equal to 6. Q equal to 2 to the 5th, then B equal to 14. And Q equal to 2 to the 8th, then B equal to 126. And after proof the theory of the proposition, we perform the experiment, and this table shows some our result. We can see we obtain some symmetric 4x4 MDS matrices effective for implementation from reasonable code. And we can see these symmetric polynomials having the constant term equal to 1. The constant term equal to 1, you can see. And you can see the coefficient of all the polynomials is symmetric. So we can obtain the corresponding symmetric MDS matrix here. Yes, this is our main result in the research. And now I will present the conclusion of this talk. In this work, we will show the way to obtain symmetric 4x4 recursive MDS matrices effective for implementation from RS code over the general field of Q, for Q equal to P to the R, and P is prime number R. And especially, we also have shown that the 4x4 recursive MDS matrices from RS code can only be built over fields of P to the R for P equal to 2, but not for P be an any odd prime number. It is also given some specific cases of symmetric recursive MDS matrices over fields of 2 to the R. These matrices are very effective for implementation and can be applied in language cryptography. It's on my result. And here is some references we use in our research. Thank you for listening, and I wish our conference great success. Thank you very much.
Thank you, Ms. Leung, for your very interesting presentation. And now Q&A. Question, please. Oh, yes. Please, microphone.
I listened your presentation, and I have one question. Why the MDS matrix, recursive matrix, can be effective for implementation?
Thank you for your interesting question. Why the recursive MDS matrix is effective for implementation? Yeah, you can see a recursive MDS matrix A has the form A equal to S to the M, where S is a serial matrix. And we can see the form of the serial matrix. They have almost elements equal to 0 and 1. It has only the last row with non-zero elements. So we can use this matrix to reduce the hardware circuit, and so we can save the resources when we perform the hardware implementation. And besides, we can see the inverse of the serial matrix has the same form. So when z0 equal to 1, yeah, we can see the first row of the serial inverse is the same the last row of the serial matrix. So we can obtain the low cost for implementation for all the encryption and decryption as well. It's the reason why we should find the recursive MDS matrix.
So, okay. Yes, another question. Okay, please the microphone to this girl. Practical.
I have a question for you. As I know, there are many methods for constructing MDS matrices. So why you choose Solomon codes for constructing these matrices? Thank you.
Thank you for your question. Why I choose Solomon code for constructing a recursive MDS matrix? There are three reasons I choose Solomon code. The first reason, the Solomon code is one of the most common linear code from coding theory. The second reason, RS code is one of special case of MDS code. And the third reason, we can build Solomon code very easily. So we can build recursive MDS matrices very easily too. There are three reasons I choose Solomon code. Thank you.
Okay. Yes, a question from Đào Ba Anh. Other methods to find recursive matrices also effective for implementation is correct.
Correct.
Yes. Other methods to find recursive matrices also effective for implementation is correct. So can you show us yes or no other methods to find recursive matrix?
Yeah,
okay.
Yeah, I see. Thank you for the question of Bahang. Some other methods to obtain recursive MDS matrix. In this research, we show the way to obtain recursive MDS matrix by the Solomon code. But in the practice, some authors can use some other methods. For example, they can use the exhaustive search for the recursive MDS matrix, but this will limit the size of found MDS matrix. And some other authors in the literature, they use other linear code. For example, the BCH code. But the BCH code is very complicated, so we don't choose the BCH code. Yeah, thank you.
Okay, Mr. Bang, you hear the answer from Miss Llượng. Okay, and thank you, Mr. Đào Bang, for your question. And I have a question for you, Miss Llượng. So I see in your research you used Solomon codes to construct recursive MDS matrices. So how many recursive matrices can you find by Solomon codes?
Thank you for your question. How many recursive recursive MDS matches. Yeah. In this table, we show you the total 18 symmetric recursive MDS matrices. But for further research in our team, we can find more symmetric MDS matrices because we can use the direct exponent transformation. This transformation can preserve the symmetric and recursive property of MDS matrix. So we can use this transformation and we can find a total about 136 recursive MDS matrices from this model.
Okay, so this is the future of your research.
Yeah, in the future of our research, the interesting question from Mr. Chung. I think in the future I continue to research about recursive MDS matrices, so we can use other method. For example, BCH code or other methods.
Okay, thank you.
Yeah.
Would anyone else like to comment on this? Okay, I think if nobody has anything else to ask, so let's move on to the next item.
Yeah,
Thank you,
very
Ms.
much.
Silya.
Thank you so much.
A research group from